working on IPCC reports at one authorship level or another for the last 30 years. This was different than any other one I'd been on, which I'll explain in a moment. This was the special report on oceans and cryosphere and a changing climate was initiated by the governments for I think two reasons. Number one, it's the year of the oceans coming up and they wanted a report on the oceans. And number two, there seems to be a continual demand from policymakers for up-to-date information on sea level rise and risk along the coast, because they are faced with making decisions now that need to be good for 20, 30, 40, 50 years or more into the future. And frankly, the scientific news, because of the rapid changes we've seen in understanding, has, I think, been kind of confusing to them. So the hope was that this report would straighten that out. We made maybe incremental progress in that direction, but there'll be another IPCC report coming out in about 18 months or so in the sixth assessment, where sea level rise in particular will be gone over again. The particular chapter I worked on was this one, chapter 4, on sea level rise and its implications for the coasts. And the thing you need to know about this chapter, can I assume, by the way, that my video is advancing properly? I just pushed it forward. Did you see it?
Yes, it looks good.
Okay, good. So sea level rise isn't the entire issue along the coast. We're worried about short-term events like coastal storms, episodes of extreme sea level, as we see here. And the scope of this report covered not just the physical science, but the social science, the economics, the questions of how humans are going or have been responding to risk along the coast, how they can respond in the future given future sea level rise. So it was broken into 4 sections. If you read this chapter, which I hope you will, it's the 4th of 6, it not only has a usual executive summary, but a synthesis section, which is a short synopsis of the chapter, which is expansive compared to the usual executive summary, but hits what we think are the most important high points, and has some significant figures right in there. So if you want to take a quick look at that and then delve into the parts of the chapter that really interest you, that would be an interesting way to go about it, recognizing that few of these chapters get read in the entirety by very many people. So we have the synthesis. Section 4.2 is the physical science basis, the material most of you are used to, with an emphasis on projected changes in the global and regional mean and extreme sea levels. And this is where we talk about the processes, we talk about observed changes in sea level to date and projections for the future. There are then a 3rd and 4th section, which you're probably less familiar with, those of you who are physical scientists anyway. One deals with exposure, that is being in the wrong place at the wrong time, whether you're a thing or a person or an ecosystem. Vulnerability, which is the sensitivity to damage happening, what the damages are, in other words, the impacts, and putting that together into a picture of risk. And you have to remember, the physical science part is called hazard. It is not risk. Risk is a combination of a hazard, exposure, and vulnerability, and it's affected, of course, by adaptation, which is aimed at reducing exposure and vulnerability, but sometimes goes awry and you get what's called maladaptation. And then finally, and really what's the newest part here for an IPCC chapter, is the question of how to respond, what we know about adaptive responses, where they go right, where they go wrong, and importantly, what we know about human governance about along the coast. This is really about the politics of defending against sea level rise and other coastal risk. And I think it's probably the most interesting part of the chapter if you have a broad view. So in this talk, I'm really going to focus on the part you're used to, which is part 4.2, the physical science, but with a view at the end, if there's time, to discussing the other 2 parts. Now, one of the ways to look at the motivation for this chapter, it's generally to provide useful information to decision makers. In a situation where the science, particularly the science of ice sheets, is still in flux and rapid flux compared to what we usually see even in the climate change business. This figure, which is an adaptation of a figure in Garner et al. From 2018, shows various estimates of sea level rise, and note the time axis at the bottom is highly peculiar and nonlinear. The axis on the left, the vertical axis, is meters of sea level rise. Somehow my attempt to put that on fell off. They're different dots and boxes. Rectangles mean different things, but mostly they mean the rectangles mean the 5 to 95% estimate at the time of projected sea level rise to 2100 in a high emissions case. And I'll just point among the various geometric figures to the pinkish section in the middle, which are the results of the semi-empirical models introduced by Stefan Rahmstorf and others in 2007, and which got wide traction for a while, even though it's not really based on physical processes. And the green, which are the probabilistic models, which were introduced by my colleague who's at Rutgers, Bob Kopp, and others, which make attempts to essentially use Monte Carlo type approaches to probabilize the projection of sea level rise, and which themselves have components. The components are largely process-based, but some of it, particularly the ice sheet components, in some cases are estimates based on non-process-based approaches, which I'll discuss a little later. And the thing you want to take away from this is that over the long course of 40 years, there's been a lot of variation in what experts thought sea level rise, total sea level rise was going to be. And that after reaching a minimum around the time of the fourth assessment, which generated a lot of confusion, because at the same time, a lot of evidence was coming out that ice sheets in particular were changing rapidly and making an unexpected contribution to sea level rise, we see a gradual rise in the projections themselves. And although some of these bars are basically what IPCC calls a likely range, the 17 to 83% probability range, you'll notice that the bottoms of the bars, whether it's 5 to 95 or 17 to 83, are going up too. So that basically means, and the means are going up, that basically means the projections have been drifting upward, and quite a bit upward. They've now, in some cases, exceeded 2 meters. So that one of the key objectives of this report was to bring some organization to this otherwise what might seem a sort of chaotic scene to policymakers. I want to point out 2 other things at this point. On the far right, we see the projection from this report, which is called SROCC for short. The IPCC likely range, or 17 to 83%, reaches as high as 1.1 meters. In the high emissions estimate, about a half, or 0.6 to 1.1 meters, which is about 10%, 13% higher than in the 5th assessment report, but nowhere near as high as some of the probabilistic estimates. We'll explain why a little later. Then a paper, which I was a co-author on, using expert elicitation, came in closer. That's the light blue rectangle that says 17 to 83% on the far right. That came in quite a bit closer to where the probabilistic estimates are, but again, above where the process-based models come out. And that should lead you to think, what's going on here? We have experts who think that the models are not quite encompassing the whole range of probability. That wouldn't be a surprise, because IPCC's estimates leave off at 83%, basically. That leaves 17% worth of probability, within which there's a lot to play with, and where there can be reasonable disagreement among experts. Still, the expert range, like what they would call the likely range at IPCC, is itself quite a bit higher when you draw on a larger band of experts than wrote the IPCC chapter. And that has a lot to do with IPCC's particular methodology for determining uncertainty. The highlights of the chapter, and this summarizes everything I'm going to say later, is during the 20th century, sea level rose about 15 centimeters. There's been another 5 or 6 centimeters since then. The rate of sea level rise, about close to 3.5 millimeters per year, is now about twice as fast as it was for the 20th century average, and it's still accelerating as far as we can tell. The extreme sea level events, and this is to me the most important nugget in the physical science part, extreme sea level events which were rare in historical times, and those are events that occur during high times or storms where you get storm surge, will become more and more common as sea level rises. That is a particular flood level, you might say, although there is a difference. A particular extreme sea level at a coastal tide gauge is a better way to say it, will occur more and more often as we go through the century, and that this century, and that by 2050, 30 years in the future, many large coastal cities and other settlements will see their historical once in a century event occur in terms of extreme sea level occurring once a year or more frequently. Once a century event occurring once a year or more frequently. And by 2100, that was by 2050, by 2100, most tide gauge locations along the coast will have achieved the status of having their once in a century, their previous historical once in a century event occurring basically more than once a year. And that begs the question of what about the once in 1,000-year event, for instance, which we didn't go into. I want to put an asterisk on that to note that in some places, a once in a century event is very damaging, like along the Northeast coast. In other places, some places in the tropical Pacific, some places in the US, on the West Coast, the damage would be more limited, but still significant. We'll go into that in a minute. So here is some material you're probably quite familiar with in terms of GMSL, global mean sea level, and talking about the long-term trends. The primary contributions are from steric changes, primarily thermal expansion. And we use the AR5 projections. And the reason we didn't change anything from AR5 with regard to thermal expansion is because we didn't yet have the CMIP6 model projections. There wasn't much different to say. It's close to the same. The same thing with nonpolar glaciers. The literature doesn't change much between AR5 2013 and the time we wrote this report. The same thing for the surface mass balance and dynamic aspect of what's going on in Greenland. However, for the Antarctic ice sheet, there's been a significant amount of new literature, some of it new process-based modeling. So that's the component of our basis for projection that is different from AR5. Changes in land water storage, largely not connected to the climate in any direct way, is again taken as the same as an AR5. Here is the one of those lovely IPCC figures, which you look at and say, I should be looking at something else. This is too confusing, but basically has all, or I should say, almost all of the processes that are critical, that are important. Some of these processes, and this is the important point here, are very local, like subsidence, and as a result, they do not figure in the calculation of global mean sea level rise directly, but we do take some of them into account in projecting future regional sea level. This is extremely important because regional sea level is what you need to understand how sea level extremes will change along the coast. And here at the bottom, we have an indication, I'm having a little trouble with my mouse today, of what happens, what contributes to sea level extremes. We get mean sea level, and of course, sea level rise, it changes in mean sea level, the astronomical tides, storm surge, if there's a storm around, wave setup as the wave approaches the coast, and then the action of the wave against the coast as it sort of smears up along, for instance, a beach and reaches a higher terrain. All of that needs to be taken into account to get a truly accurate picture of what the changes in extremes will be. We did not take into account wave setup or swash in our estimate. It's too local, too particular. What we did take into account, though, are the contributions to regional sea level, which I'll get to in a second, and the effects of storm surge and astronomical tides. One particular feature I want to bring your attention to that you've heard lectures about in this lecture series, I believe, is the question of the stability of the grounded ice in Antarctica. This is a picture, a cross-section of the Thwaites Glacier. And we have here, the concern is the question of what's called the marine ice sheet instability. The question of whether warm ocean water, circumpolar deep water, the dark patch here, creeps up on the continental shelf. We know it does in certain places, like the Amundsen Sea area, gets under the ice shelf, which is a floating piece of ice that extruded off the continent, and which buttresses the grounded ice and keeps it from dumping into the ocean and contributing to sea level rise. And whether that's an unstable relationship where if you make a change, either through increasing flotation by sea level rise, a minor factor in the future, or warming and thinning the ice shelf, causing an instability to happen where the ice shelf moves forward, thins further, where the warm water gets further under the bed, under the ice shelf. The ice shelf extrudes outwards, and this creates a feedback process which keeps ice moving forward into the ocean and keeps warm water moving under, as long as the bottom of the ice sheet is on a bed which is sloped, I should say, downward toward the center of the Antarctic continent, which is all the way on the left here. And so that process is called marine ice sheet instability. It is, we've seen examples of it with the collapse of small ice shelves up on the peninsula, and is believed to be a process which is possibly already underway, possibly irreversible on the Thwaites Glacier. There's another process called ice cliff instability, marine ice cliff instability. This was brought up in a series of papers with Dave Pollard, Rob DeCanto, and on one of them, Richard Alley, starting in 2015, and then the paper made a big splash in 2016. And this could vastly accelerate through a combination of hydrofracturing and ice cliff instability, the collapse of these ice shelves, and roll forward the timing of loss of grounded ice due to the loss of buttressing. In our report, the paper that reported this in 2016, by that time, Rob, who was on our chapter, had realized that the surface melting of ice shelves had been included as too fast a process. And so the current estimates that he's talking about are quite a bit slower for that process, for the melting and marine ice cliff instability. That is surface melting still governed by the warming beneath, in all likelihood, throughout this century. Therefore, we did not include estimates from that paper in our projection, and that's one reason why it's less. The results are lower than many of the probabilistic estimates, which do include that rapid marine ice cliff instability. Here's this is our global mean sea level rise observations. I've just circled all the way on the left the recent observations. What's important here is that the sea level budget is close to being closed, or perhaps is closed, depending on your taste for what the uncertainty really is. And that's the total contributions from adding up the processes are very close to what the observations tell you from satellites and satellite altimetry and tide gauge measurements. And you'll also see that the modeling, which I'm suspicious of because I know the quality of the ice sheet modeling, particularly for Antarctica, is not very good at this point. Still a lot of uncertainty, comes suspiciously close to the observations. And I think that's a total accident. And you'll notice the wide error bar on the uncertainties on the in the lower red circled entry on the far right, sorry, where it says 3.54. But nevertheless, despite those uncertainties, the three ways of looking at the problem are in fairly close agreement. And The trouble is that for the future, we are confident that the ice sheet contribution, Greenland plus Antarctica, which is now is somewhat more than a third of the total annual sea level rise contribution, is going to continue to increase relative to thermal expansion, and that the glacier contribution eventually will slow down, particularly its relative contribution, so that what we're looking at is the element which has the largest uncertainty is the one that we believe will come to dominate sea level rise over the coming decades. Now, to get back to what's important for understanding extreme events along the coast, we want to talk a little more about regional sea level rise. In the IR5 report, there was very little emphasis on regional sea level rise, and the presentation was, one could say there was an error in it, one could say it used a distribution to represent this regional sea level rise, which was inadequate to the task. In any event, it was a small section and not thoroughly discussed. We made this a center point of the report, and as I said, I think it produces the highlight of the physical science. The reasons for regional variation in sea level rise compared to the global mean are that thermal expansion and ocean circulation contributions are regional. That is, they tend to make water, pile up water in certain places compared to others. If you're talking about ocean circulation, you have different depth variation of ocean temperature, so you get variation in the thermal expansion. And so it's the regional aspect of sea level rise at different places along the coast is a contemporary climate-driven process. Then you have a series of interesting processes referred to as GRD, gravitation, rotation, deformation, which is a set of changes in the solid Earth response, or the response of Earth's mantle to the changes in the distribution of ice and water that come about because largely of the melting of the ice sheets. So ice sheets are large enough that they have a measurable gravitational attraction. There's a measurable gravitational attraction they exert upon water. This creates a distinct pattern of distribution of sea level around Earth, and it's called the fingerprint. And that fingerprint will change as the ice sheets lose ice and their mass decreases, resulting in essentially letting go of the water, which then that signal of that the lower gravitational field will diffuse around Earth. And that's therefore indirectly a contemporary climate-driven phenomenon, and it's significant. And we took account of it in calculating the regional coastal variation in sea level. Then there's the glacio-isostatic adjustment, which is a paleoclimate-driven phenomena, a relic of the retreat of the Laurentide ice sheet, primarily in the Northern Hemisphere, and that is a significant contributor along the east coast of the United States. Those contributions are included in our projection of future sea level rise. What is not included are the non-GRD components of subsidence. And these in some locations are very important. You wouldn't want to talk about the future sea level rise around Jakarta unless you knew what the subsidence was going to be. Same thing with Alexandria and a lot of other places along the coast. But this is a hard thing to project. It requires a lot of local knowledge, and even then a lot of projection about what policymakers will or will not do. It's not feasible to create scenarios for all the important places along the coast, which would take all the possibilities into account, so we didn't do it. And instead, we focused on the Antarctic ice sheet component as the major effort in reducing uncertainty. So again, we used all components except including the Greenland ice sheet surface mass balance and iceberg discharge, the dynamical component, in estimating future sea level rise. And again, little change in those components to date from AR6. We're waiting for CMIP6. From AR5, we're waiting for CMIP6 and AR6. As we said, ignored non-GRD subsidence. And when looking at the Antarctic ice sheet, where the surface mass balance, because it's cold, is rather less important. We're focused mostly on the dynamical component. If you want to know what the changes in the land ice, which are what effect sea level rise will be. And we relied on 3 different models. If you're interested in the details of ice sheet models, I've listed here what the capabilities and limitations of the various models are. You can go back and look at it later. Basically, these are 3 different, what you might call incomplete slices on the problem that are all simplified in one way or the other. Either in the atmosphere, ocean forcing, and it isn't easy to, we don't know very well what the ocean forcing is, at least near the coast. We have difficulty melding that with the ice-driven processes, with the ice response processes. But probably the PISM model, the parallel sheet model, does as good a job as anybody can do today. Then there were various other models which contain various other frameworks and simplifications, which are, and all of these, however, are basically process-based models, and we included them in our estimate of what Antarctica would do. And if you look at this table, again, too many entries, so I've tried to circle a few of the key ones. And if you drop down to Antarctica, and I've focused on the high emission scenario, RCP 8.5, but of course all the entries are there for the period. Looking over in the far left, Antarctica 2081 to 2100, you see that the contribution is 0.10 meters, plus or minus about 10 centimeters, give or take. This is about twice the contribution, at least at the high end there, that was estimated in AR5 using a model which it was a mixed process-based and expert judgment combination, using a probabilistic Bayesian framework, and credited to my former postdoc, Chris Little. Some of the other models which we used in this report didn't quite make the peer review cutoff, but were almost available at that time. So probably we could have used a slightly more process-based approach, but we weren't allowed to because it wasn't in the literature yet. And the interesting part to me here is if you look up to the Greenland components and add the surface mass balance and dynamical part together, and forget for a minute that these uncertainties are not really independent, you'll see that the Greenland and Antarctica components are, quite comparable according to these projections in the high emission scenario for late in this century. And that's interesting. A lot of people have tended to drift over to worry more about Antarctica than Greenland. A lot of people never thought Antarctica was going to be a big deal and got stuck on Greenland. I think everybody has to do a careful reconsideration of their view on this. And when you get to the bottom, you get the ultimate number that I talked about at the beginning, namely global mean sea level rise in 2100 of somewhere from between about 0.6 and 1.1 meters in the high emission scenario. And in the medium emission scenario, the RCP 2.5, considerably lower. And in the low emission scenario, RCP 2.6, which is frequently taken as to be an indication of what one would have to do to reach the Paris targets of 1.5 or 2 degrees, you see quite a bit less sea level rise, which is an extremely important point with regard to adaptation potential. If you then slide along the last line in the table, the rate line in millimeters per year, you see the rates in the Paris Agreement target are relatively, they're not too far off what today's rate is, average is about 4 millimeters per year. But the median rate when you get up to the RCP 8.5 is 15 millimeters per year in our projection. That's 5 times the rate we have today. And we're having trouble adapting along the coast to sea level rise in many places. It's quite a stretch to think that it's going to be a piece of cake to deal with this in the high emissions case. I do want to point out in all fairness that RCP 8.5, which some people were erroneously taking to be a business as usual trajectory, it was never meant that way. It's a it's really a high-end emissions pathway. Lately, there's been a re-emphasis on the fact that it shouldn't be taken as business as usual, so keep that in mind. Nevertheless, there's trouble in the future, even at current rates of sea level rise. So just think about 5 times the rate. If we then go on to look at this graphically, I'll introduce 2 other concepts. One is, this, by the way, goes through, this one idea here is it goes through 2300. And notice that in the low emission scenario, the blue one, RCP 2.6, the low curve, sea level rise, the rate of sea level rise slows, sea level tends to stabilize out, but way out. You get in either the red, which is the 8.5, or the blue, 2.6, you get continuous and accelerating sea level rise, even in the 2.6 scenario, right through 2100. But 2.6 does start to slow down. But RCP 8.5 continues to accelerate. The curve continues to steepen right through 2300, and in fact beyond, if you extend the RCP scenarios. So that's troubling right there. The other thing I want to point you to is in both the, on the far right-hand side of both the small inset panel, which is the sea level rise through 2100, and the far right-hand 2300 estimates, you see these 3 different, at least in the inset panel, 3 different ways, not process-based or not entirely process-based, for estimating sea level rise. The B19 is the Bamber et al. Expert elicitation I talked about a minute ago, more than a minute ago, 35 minutes ago, that I was involved with, as was Bob Kopp and a bunch of others, that the probabilistic are the probabilistic approaches. In this rendition, since we took the Canto and Pollard out, these probabilistic estimates are truly just a way to probabilize the uncertainty band and get a quantitative uncertainty band. And these show therefore a lower range of estimates than the ones from the Garner et al. In the first slide. I showed the green rectangles in the beginning. And then there was a sensitivity estimate based on, I think, emulating a bunch of process-based models by Schlegel et al., which gives an upper end. And you'll notice that the SROCC estimates for IPCC, for RCP 2.6, the blue, RCP 8.5, the red, come in again a little bit lower than the expert elicitation. They come in close to what the probabilistic estimates show when you throw out the DeCanto and Pollard 2016. And they come out well below the upper, what you might call an upper limit determined by Schlegel. It's important to note when I talk about the DeCanto and Pollard 2016 paper that they are working on further estimates, and that the bad news that the original paper brought you for 20 in the 2016 paper is just pushed off by a few decades. So it's not a get out of jail free card. It's just a get out of jail free card if all you're worried about is the 21st century sea level rise. But if you've got this longer 2300 perspective, they apparently do find a rapid increase due to the Mickey process, the marine ice cliff instability later. This is another way to look at these findings. It shows the different components of sea level rise due to the contributions due to Greenland, Antarctica, and glacial masses, the ice components. And you could see them. I'll leave this to you to look at separately, but it's a nice way to look at the individual contributions to either the low emissions or high emissions scenario.
Can I interrupt you for one moment, Michael?
Yes.
There's a question in the chat from Allegra. So sorry to put you on the spot, Allegra. Would you mind unmuting and asking?
Sure. So some old work that I did with colleagues for the early Holocene shows that the Laurentide ice sheet was melting at that time at about a rate of 1.3 centimeters per year. am I reading that previous figure right to say this is what our RCP 8.5 scenario is for year 2100?
Well, it gives 15 millimeters per year, so do the math.
So that would be a yes. Do we think that the early Holocene is an analog for modern sea level rise potential?
I don't want to push it too far because there are a lot of ways in which it's different. I'll just say that this is what you get if you use the best process-based models of Antarctica that we have today. Stay tuned for AR6, where there's still controversy about exactly what they're going to do. Where there's a range of estimates, and I, didn't bother to think about the paleo analog in coming into this talk. I spend more of my time on the on the LIG, but in that sense, yeah, it could be a good analog. It's not very helpful, of course, in terms of what do we do with a built-up coastline? Can we and settle civilization? How do we deal with these high rates of sea level rise? That way the analog doesn't help. As a physical science analog, there may be something to it.
So when you say the LIG is an analog, what do you mean? Like understanding why we had so much higher seas in LIG?
Yes, I mean that, we did some work on that led by Bob Kopp now about 10 years ago. You can look up the paper. Okay, does that more or less answer, is that non-answer answer your question?
Well, I mean, the Laurentide was not a marine terminating. That was just a direct surface mass balance flux that caused it. And the radiative forcing on that was within like a factor of 2 of what the modern radiative forcing is supposed to be on Greenland. So I'm still curious on why the rate is only, like, our biggest worst case scenario seems kind of low. That's, I guess, my real question.
It is, yeah, okay. So that could well be. We don't know what happens when an ice sheet that big starts falling apart. All I can tell you is what's incorporated in our models, which leave a lot of stuff out. As of today, this is the highest, the error bar I think was up to 20. This is 20 millimeters per year. This is what we get out of it. Would I be shocked if it wasn't enough, because the marine ice cliff instability actually allows things to go a lot faster once grounded ice starts to be lost? Would I be surprised if once warm water starts getting under the ice shelf, we not only get instability, but the warm water, as Terry Hughes said decades ago, carves the heart out of the West Antarctic ice sheet? I wouldn't be surprised at all. So if you want to look at this as a bottom, a lower estimate, and take the other estimates more seriously, that is the probabilistic estimates, that's be my guess. If I were a policymaker and had to make decisions for 30 to 50 to 100 years from now, because I was thinking about building surge barriers or evacuating, not evacuating, it's the wrong word, managing retreat of populations, to use the politically correct way to say it, I would look at those high estimates. Yes, I think it's an unsettled question. Okay.
Right. Thanks.
Okay. I'm being cautious because I'm representing the results of a report where a lot of other people were involved. My own view is take those high estimates seriously if you're responsible for other people's lives and safety and behavior. Don't run around with your mask off, is another way to say it. Okay, so again, to go back, we supplemented the usual process-based approach by using techniques that are only partially process-based, include in some cases a lot of expert judgment on the Antarctic part, particularly the statistical models, by directly using an expert elicitation for Antarctica, and by using the sensitivity study of Schlegel, all of which gave a higher estimate. And this goes right to your question, by the way. We did not resolve the timing and importance of ice cliff instability, awaiting more development in the literature. And we do make this recommendation, and this I think goes to the point you were just making, and I'll quote the report: the range of sea level rise to be considered in decisions depends on the risk tolerance of stakeholders, with stakeholders whose risk tolerance is low, also considering sea level rise higher than the IPCC likely range. That's the first time IPCC has pointed people in the direction of taking its likely range with a grain of salt, fully recognizing that decision makers care a little less about IPCC's likely range and care more about what the worst case would be. And this goes to the question about the Laurentide ice sheet. I certainly would pay attention if I were a decision maker and had to make decisions about, for instance, whether to evacuate parts of Brooklyn and Queens because they're low-lying and they're very difficult to defend. Evacuate, actually, plan retreat for, again, I'm sorry for getting ahead of myself, over many decade period, that those are things I would be taking into account now in Syria and considering how I would manage them. The regional sea level rise, just to wrap up here quickly, I want to leave some time for questions. This is how regional sea level rise plays out at various parts around the world. Some places it's not much different than the global mean, but the mean deviation is about plus or minus 30%. The standard deviation is plus or minus 30% from the mean, and that's sort of what the figure on the right shows you. And if you're interested in particular locations and how they differ, of course, the Northeast, well known in the upper left-hand corner than New York, has a considerably faster sea level rise than historically due to GIA and some other factors related to ocean circulation. Now, in getting to the short-term processes, and this is the bottom line, we took tides and storm surge. We included these in the SROCC projection. We did not include wave action. This is a schematic way to think about how you estimate changes in extremes of sea level at the coast. You've got tide gauge measurements. We use tide gauge measurements of at least 20 years in length with 70% of the data reported. We fit those to a generalized Pareto distribution to characterize the long tail and to get parameter uncertainty. In other words, if you're worried about 100-year storms, you don't see many of them, or you shouldn't in the record. So to get a good picture, you have to use extreme value theory. We applied different forms of extreme value theory to different parts of the distribution, a GPD for the tail. And we combined that with the regional sea level rise projections that I just described and used a bathtub approximation. That is, we got extreme water levels as a function of return period, but we did not let sea level rise interact with the tide or storm surge, which it turns out recently has become a very popular subject in the literature, which we probably would have addressed if it had been a popular subject at the time we did the assessment. And I'll get to that in a moment. Here are shifts in extreme event return periods. The left-hand axis is the elevation, basically the sea level, as a function of return period, which is the abscissa. And you see 4 curves on each of these stations. I just picked 4 stations that have interesting different behavior. First, focus on the lower gray curve. That's the historical data. That is, you fit that data with extreme value theory to get the overall behavior of, to get the generalized Pareto distribution, to then combine with sea level rise to get the future distribution of extreme events. And you notice the X's, each X is an event, and you'll notice going out that some of these fits are very good, like over here, Barbaroulas, Alexandria, Tahiti, a little less good. Guam, you've got this outstanding event right over there, which was probably a tropical cyclone, and not very good fit. But you still, you do the best you can with these distributions. When you then factor in sea level rise, you get the dark blue curve, which is what happens in the RCP 2.6 projection, the light blue RCP 4.5, and red, the 8.5 projection. And you can see that in all cases, what was the height of the 100-year event, for instance, increases markedly in the Guam station from 1.2 to about 1.8 meters, and it changes, and of course, rather less of a change for the RCP 2.5, and for 2.6 and 4.5. And in other words, it's a big increment on sea level, which is basically comes from adding the amount of relative sea level rise for the location of the tide gauge to the distribution of storm return periods, which we find historically using the Pareto distribution. Now, these are simplifications when you get to these numbers. The bathtub approximation leaves out that there are serious interactions among sea level rise, tides, and surge. So, for instance, for storm surge, if storm surge is riding on a higher sea level as it approaches the same bathymetry near the coast, it gets less oomph from friction with the bottom. That both slows it down, but it also makes it occur lower. And the combination of those two, in most cases, not all cases, yields a lower overall extreme sea level. There are exceptions to that. The point is that too has to be calculated location by location, depending on the particular conformation and bathymetry of the coast. Tide gauge locations are not all anywhere near the locations that you're interested in. Surabaya in Indonesia has a population over 1 million. It's not a mega city, but it's a big place. But the nearest tide gauge is about 100 kilometers away. What we don't know for sure how good the information is to apply to Surabaya. So there are now interpolation methods being developed. My group's working on it. Others have been working on it. And there are a couple of papers in literature on it. And you always keep in mind high water at the coast at the location of the tide gauge, even if it's close to the coast, is not identical to a flood level, because the minute that water gets very close to the point you're interested in, you may even be just a few kilometers away from the tide gauge, you can get quite a different reading as the water hits the land. And then as it goes inland and starts interacting with a complex topography, like think Manhattan. It's not easy. There are hydrodynamic models that do this with sufficient resolution. However, the elevations near the coast that you feed into these models are very uncertain, as the work from Climate Central about 8 months ago showed. And secondly, the hydrodynamic models do not capture tropical cyclones well, and that's one reason why we stayed with the tide gauge approach. Finally, here are our calculations of the amplifications. This graph, this figure is a little bit, it kind of elides the true differences because the shadings are not, they make it hard to read. And we struggled with this one and wind up not doing very well. But if you look at the tables there, and you can get for a particular location, particularly in the supplementary material and some of the related papers, you can get a better idea. The amplification of the return frequency means if a factor of 10 amplification on the 100-year, the historical 100-year event means it comes every 10 years. A factor of 100 amplification means it happens every year or less. So here, there goes my mouse again. Here at the bottom, that shade going from yellow to orange is starting into red is a dot, which tells you there's a factor of 100 amplification, which means, again, the historical 100-year centennial event is now an annual event. And I would look at this figure two ways. You could look at the difference between RCPs for either mid-century, the right-hand column, or the left-hand column, or the right-hand column, end of century. And you notice for any one RCP, there isn't a great deal of difference. I'm sorry, for any one, either period, mid-century or end of century, it doesn't make that much difference when you go from RCP to RCP. In mid-century, that's because the RCPs haven't diverged very much in terms of their effect on sea level rise. So of course, you're going to get about the same result. And the result is that many, although not most, stations around the coast have their historical centennial event happening at least once a year, if not more often. And the right-hand column indicate there is a substantial change from the right-hand column. When you go from left to right, you get, by end of century, most of the tide gate locations along the coast move towards this historical centennial event becoming the annual event. That's a huge change. It really has to be thought about carefully in terms of what we're going to do to adapt to that kind of change, given all the uncertainties I talked about. And remembering, as I said right at the top, that for some places, the historical centennial event is a high tide. That doesn't mean that they didn't build right up to high tide because they know it only happens once a century. It does mean that the fraction of settlement might be smaller than, say, when it happens along the east coast of the United States, where you're talking about the effect of a tropical cyclone. And just to conclude by talking about what can be done about all this, there are plenty of approaches. This is section 4.3 and 4.4 in the chapter. There is plenty of ways to adapt. None of them are easy. Some of them are more difficult, more expensive than others. Protection, building, pouring concrete basically, or land, earthen embankments, a combination of these things with other types of protection is the most reliable, but the most expensive way. It's economically sensible in places that are dense, but it's not economically sensible, at least in places that don't have high population densities. And we can't afford to do it in most places, I think is the straight answer. And when I say we, I particularly mean the United States. Accommodation means taking actions which let you more or less stay in place, like raising buildings, building new buildings so they're periodically floodable, building sidewalks which drain water away quickly, that kind of activity. They tend to be also relatively cost effective, but at some place their value runs out. With enough sea level rise, high enough extreme events, they don't help. Ecosystem-based approaches like enhancement of wetlands are helpful. We don't know much about the cost effectiveness. We don't know as much about how long you can stretch the value before you have to go to hard protection and accommodation. Anyway, there's advance, which is do what the Netherlands did and just keep building out into the ocean, or they used to do. That's an expensive proposition. Cities like it because it adds new revenue from real estate value, but it's very expensive. And in most instances in the United States recently, there have been proposals which are mostly real estate development proposals and don't really do the optimum in terms of coastal protection and people protection. And finally, there's managed relocation, which I know Klaus will tell you the same thing. We have to get serious about this. This is something which, like building a surge barrier, which takes 30 years to plan if you're good at it, and maybe 50 years to plan and implement, maybe 50 years if you're lousy at it. It's difficult to get big projects done in this country. Managed relocation is also not easy. It will run into a lot of political opposition. There are ways to do it which minimize the opposition and make it easier by starting voluntary and starting with buyouts. How much we can afford, we don't know. The whole coastal protection system needs to be renovated to rip away the incentives for bad behavior, like the National Flood Insurance Program, which is a bankrupt disaster at this point and gets people to do the wrong thing. All of this needs to be looked at. And given the timescales we're talking about, 30 years for some very bad stuff to get, that's already bad, to get much worse, we really have to start paying attention to this right now. And finally, probably the most important message to keep in mind, it's easy to talk about doing expensive projects, but it's the people with the highest exposure and vulnerability that have themselves the lowest capacity to respond and often live in poor places that don't have the resources. In this country, most of the resources are in the federal government. There's much less in the state and local level, and we have to figure out how to rectify that system. Thank you. Took a little too long, but I can stick around a little longer too to answer any questions you have.
Thank you very much, Michael. That was a fascinating talk. I should get some canned tapping or something to end.
It's okay.
It's strange at these times. So there's an interesting discussion going on in the chat that is going on at the moment. So I think Johnny Kinglake was someone who was commenting. I was wondering if you would like to ask a question or make a comment this time.
Well, yeah, I wasn't really necessarily a question. I was just contributing to that discussion which Allegra started about the differences between the early Holocene Laurentide and waste. And my just immediate thought was, of course, maybe the processes are slower. We have fewer marine terminating areas, but you just have a larger ice sheet, which has potential to contribute sea level rise at a comparable rate to waste, despite some of its slower processes. And then might contribute to something about the proportion of the ice sheet which was marine terminating at different times. Fascinating talk, though. Thank you.
Thank you. Yeah, the chapter didn't go into the Laurentide analog. We did go in some depth into the last interglaciation in the Pliocene, and thus my reluctance to give too sharp an answer on that question. But the idea that we don't know a lot about some of the aspects of ice sheet behavior needs to be taken seriously, and I think there's totally inadequate resources going to dealing with that problem.
So, if I this is Allegra again, sorry. If I can just ask a question about your last couple of slides about policy adaptations. So, so in New York City, like or New York State or New Jersey, where you're familiar with, how would you alter the ULERP process to adequately take into account the risk of sea level rise?
So for people that don't know, the ULERP process is a local planning. It involves communities essentially in local planning of projects. I think you shouldn't successfully try to rebuild the relationship of a city like New York or Philadelphia or Boston to the coast unless you involve people directly in the decision making. And if you don't involve them, how are you going to convince them to get out of the way? Are you going to move the army in, close off neighborhoods? Look at the problem we have getting people to wear masks. How are you going to get people to move out of neighborhoods they've been attached to all their lives if they're not involved? But if you get them involved from the beginning, if you realize that the average homeowner has a 30-year mortgage and the value of their property may be decreasing to them in some sense over time, their children may not care if they live in the same house. You have to have a way to deal with these situations which are sensitive to individual concerns, yet don't maintain the fact that the city, for instance, no matter what city it is, maintains these places by building infrastructure, maintain the infrastructure like sewage, water supply, etc., highways. So the only way to get around that problem is not to act in an authoritarian way, but to start early. And we should have started a decade or two ago and start engaging people in the process of things like relocation or accommodation or protection, because even protection means you're leaving somebody out and they're going to scream about it. There is no way to do this without doing it in a fashion which handles the politics well. And community based planning is part of that.
Thanks. I was actually I was thinking not just of managed retreat, but also New York City lately has, and it came up actually during the IPCC 3 meeting, that the meeting location, the density there on ground that was vulnerable to sea level rise was greater than it had been the last meeting. So that's kind of what I was asking about.
Well, I give you the same answer. There is no, any of these measures involves, in a densely populated area, involves making decisions that are inevitably going to put somebody, hurt somebody essentially. You know, you can't avoid that. You're going to make a big change. And the way of making that change has to involve some community discussion. And that's the essence of the Euler process, in my view.
Sorry to jump in, Michael. I've got to leave to another meeting, so I hope it's okay. I've made you the host of this meeting. Thank you again for a fascinating talk.
Okay, sure.
And I hope the really interesting conversations continue.
Okay, if anybody wants to ask any questions, I'll take the hand. I see that Klaus has got his hand up. You can ask to unmute if you'd like. Klaus, I think your mic is on. Go ahead.
No, I just unmuted myself.
Good.
Well, I'm always worried when the NPCC has values in excess of 2 meters for 2100, and even added in its last report a value that was 8 or 9 feet, so getting closer to 3 meters as a possibility without assigning a probability to it for the 2100, versus when you come out with a report like this, there will be always people say, oh, those scientists don't know what they are talking about, so why should we go for those high values?
Yeah, so, you know, that's why we try, look, it's not revolutionary, but we tried to put the higher values in our report, and IPCC never did it before. And we have a clear statement that people ought to use the high values if their risk aversion is such that it justifies looking at the high values. For instance, if they're planning a project that has to last for 50 years and costs billions and billions of dollars, they'd be wise to use the high values.
But your values are still substantially lower than the NPCC has.
I was on NPCC, and Bob Kopp and I and Vivian and a few others developed those high values. Yeah. And the question we asked was different. You know, we asked how high could it get, if you think about all the processes. It wasn't how high, what's the 95%, you know, what's the 1 in 20. We were going beyond that, so that's like a 1 in 200 value. And we may not have been clear enough about that, but you know, I personally believe in trying to quantify where possible and in the probabilistic approaches. And it puts a premium on reminding people that you know, the 5 to 95% range is not the same as the 17 to 83. It's not the same as the 1 to 99 range, and they're all different. And policymakers have to understand that.
But the NPCC put probabilities on it. Maybe the 90 percentile was the 70.
No, I don't think we put I don't think we put a probability on the Antarctic, the high estimate for based on the high Antarctic estimate for rapid ice sheet loss. I don't think we put a number on it. And when we did, Bob and I did informally estimate a number, and it winds up being, you know, 1 in 100 or 200.
Yeah.
It's possible we didn't communicate that effectively. Yes, that's possible. This is tough stuff.
Okay, enough said.
Johnny Kingslake, why don't you unmute?
Hi, thanks. Yeah, I was going to maybe ask about some of those those processes which could contribute to those high-end scenarios. So a lot of our work has been about surface hydrology of Antarctic ice shelves, and we make the case that we really, the little bit of information we have about future melt rates on Antarctic ice shelves suggests that we're going to get to points where ice shelves have collapsed because of meltwater over large proportions of the ice sheet. And I missed some of the details of your discussion of where DeConto and Pollard, they had predicted melt rates, very high melt rates too early, I think, in comparison to other predictions. Yeah. I think you were saying. And I guess my only question was going to be about that. And also people talk about the MECE, marine ice cliff instability, but also just ice shelf collapse on its own seems to be something which doesn't get mentioned as much as it could do, given that's the observation we've seen in the peninsula.
Yeah, well, first of all, I'm a little reluctant to talk about Rob's work since he's not here.
Mhm.
And some of it is not published,
I
but
see.
he has talked about it at meetings. And my understanding from him is that the newer estimates they have, which reduce the speed at which the surface melting of ice shelves comes on, pushes off the nonlinear, sort of the rapid acceleration of ice loss into the early years after 2100, maybe starting around 2025, 2030, something like that. And it's because they based their estimates on one paper. I can't remember the entire story, but basically they used an estimate which is no longer regarded as realistic. And I urge you to contact Rob for the details on that. But the bottom line for what we're trying to project here is that the 2016 paper was probably too aggressive in representing the effect of surface melting on ice shelves. On the other hand, I have to say that the amount we know about the dynamics of ice shelf fracturing is not a lot, and there could still be more surprises there. Okay, I am going to have to go and not seeing any other hands. I think that's a good time. Thank you very much for listening.